Hi friends, this is Deeksha with my friend Sushmita. In this video, we have a presentation on real-time operating systems. And now let's get started. Firstly, let's see the objectives of this presentation. What is real-time operating systems? What are different types of operating systems? How to distinguish between hard and soft real-time systems? Defining the characteristics of real-time systems. Describing the scheduling algorithms in hard real-time systems. The three major things to be known here in this presentation are what is real-time systems, what is operating systems, and what is real-time operating systems. Now let's get into the details of real-time systems. A real-time computing system is a system that is able to execute programs reliably with very specific timing requirements. We can also define it as a system is said to be real-time if the required task is completes its work and delivers its services on time. Real-time system plays a vital role in many science and engineering projects. Example, robot cruise control system. Cruise control system is a system that automatically controls the speed of the motor vehicles, and this is also used in anti-brake systems. Most common real-time systems we come across in our daily life. They are desktop operating systems and real-time operating systems. Desktop operating systems. Operating system is in control at all times and runs different applications. Operating system runs in different address spaces, whereas the real-time operating systems are operating systems and embedded software are integrated. Embedded software starts and activates the operating systems, both run in same address space. When compared with desktop operating and real-time operating systems are less protected. Types of real-time systems. The three major types of real-time operating system are safety critical system, hard real-time operating system, and soft real-time system. A safety critical system is a system which leads to suffering results in case of failures. They are weapons systems, anti-lock brake systems, flight management systems, health-related systems. Hard real-time systems. The task must be completed within the specified time frames. Critical real-time tasks be completed within their deadlines. Soft real-time system. Tasks are completed as fast as possible without having to be completed within a specified time frames. The examples of hard real-time system is rocket payload and ABS. While coming to the examples of software real-time systems, they are internet telephony, multimedia system, DVD. Hard real-time system versus soft real-time applications. Here we have a diagrammatic view of hard real-time system and soft real-time system. The major difference is the deadline. While coming to hard real-time systems, the task is completed before deadlines, whereas in soft real-time systems it may take more time after deadline also. Let's see the components of the real-time systems. Various pieces of software and hardware are needed to build a real-time systems to start and finish. The components of this real-time system are real-time operating system, development tools, input and output drivers, rugged hardware. Let's see what is an operating system. A program that acts as an intermediary between a user of a computer and the computer hardware is known as an operating system. We can define it as also as the software that supports a computer basic functions such as scheduling tasks, executing applications, and controlling the peripherals. Let's see the goals of the operating systems. It executes the programs, solves the problems easier. In this type, the user can use the system more conveniently. The hardware of the system can be used in more efficient manner. Let's see what an operating system handles. The main things that an operating system handles are memory addressing and management, interrupt and exception handling, process and task management, file system, timing, process scheduling and synchronization. Let's see the examples of an operating system. The three major types are single user single task. The example is Palm operating system, single user multitask, that is Microsoft Windows and Mac operating systems. Coming to multi-user multitask, the example is Unix. Let's see the abstract view of the system components. Here we can see that different users are using the system and application program simultaneously. We have n number of users, and these the system and application program is connected to the operating system, and that is in computer hardware. Let's see the details of these. Let's see what is the computer hardware. The computer hardware is which provides the basic computing resources, that is CPU, central processing unit, memory, input and output devices. Coming to the operating systems, it controls and coordinates the uses of the hardware among various application programs from the various users. Let's see what is system and application program. This defines the ways in which the system resources are used to solve the computing problems to the users. That may consist of a compiler, database systems, video games, business projects, etc. The users may be of different types. The users may be the people, machines, or some other computers. Here we have the definitions of hardware, operating systems, application programs, and the users. Let's see the system characteristics. The system characteristics are single purpose, small size, inexpensively mass produced, specific timing requirements. Let's see the details of these characteristics. Single purpose. Here the PC designed here is supports single purpose. It reflects on single purposes and it is very simple. Small size. In the existing environment, the physical space is to be reduced to use it more efficiently. So CPU power and memory available is less than the standard PCs. Real-time systems run on 8 or 16-bit processor or less than megabytes of the memory. Specific timing requirements. Real-time operating systems meet timing requirements because whatever is the task we need to complete, the main thing we need to keep, the main thing we need to remember is the timing, the deadline. We need to complete before the deadline. Here, by using the scheduler and algorithm, it gives a real-time process the highest scheduling priorities. Priority of scheduling task does not degrade the overtime. It just gives the importance what task should be completed at what time. Techniques for addressing time requirements minimizes the response times to the events such as interrupts. Now we came to the main topic, that is what is real-time operating systems. This is often used as a control device in a dedicated application such as controlling scientific experiments, medical imaging systems, industrial control systems, and some display systems. Here we have well-defined fixed time constraints. Role of an operating system in real-time systems. Standalone applications. In standalone applications, often no operating system is involved. Microcontroller-based embedded system is used in standalone application. Some real-time applications are huge and complex, and the problems are multiple threads, complicated synchronization requirements, file system, network, windowing support. Operating systems primitives reduce the software design and time. Let's see the taxonomies of real-time operating systems. They are small, fast, proprietary kernels, real-time extensions to commercial time-sharing systems, component-based kernels, university-based kernels. Small, fast, proprietary kernels. They come into two varieties, and they are homegrown and commercial offerings. These consist of usually used for small embedded systems. They are typically specialized for one particular application. They are typically stripped down and optimized versions. They have fast context switch, small size, limited functionality, low interrupt latency, fixed for variable sized partitions for memory management, and PICOSI 8 and PSOS micro C. Let's see the details of component-based kernels. The source consists of a number of components that can be selectively included to compose real-time operating systems, and they are a hardware abstraction layer, real-time kernels, interrupt handling, exceptional handling, choice of schedulers, thread support, rich set of synchronization primitives, timers, counters, and alarms, choice of memory allocators, debug and instrumentation support. Let's get into the details of these components. Hardware abstraction layer. Hardware abstraction often allows programmers to write device-independent, high-performance applications by providing standard operating system calls to the hardware. Real-time kernel. This is also known as real-time Linux. Interrupt handling. It is also known as interrupt service routines. It is used to handle high-priority conditions. Choice of schedulers. It is nothing but selecting a particular schedule based on our choice or interest that may be based on priority or time constraints. Thread support. Threads enable a program to execute across several processor cores. The implementation of threads and process differs from one operating system to the another, but in most of the cases, a thread is a component of a process. Rich set of synchronization primitives. They provide a good set of hardware and software constraints for the synchronization. Timers, counters, and alarms. These are set to note down the timing, the deadlines, worst time, best time, and all these. Choice of memory allocators. It is based on our choice, that is maybe on the priority. Debug and instrumentation supports. Here it debugs all the errors and provides all the software and hardware requirements to the execution of these particular tasks. Let's see the requirements of RTOS. RTOS must be predictable. We have to validate the system. We have to validate the operating system calls and services. We must know upper bounds of execution time of a system calls. We must know the memory usage. We must have a static bounds on memory layouts. We should know the size of the data structures, examples, queues. We should also have the information about the fine-grained interrupt control. Now let's see, why do we need real-time operating systems? In the present world, for many engineering and scientific purposes, or for running a measurement or control programs on a standard PC with a general purpose operating installed. Let me give a clear explanation of this point. This is nothing but a general PC with simple operating systems is not suitable to execute or run a program and control a program. Some types of Windows are unacceptable, which have more depth of subject. At any time, the operating system might delay execution of a user program for many reasons. That is, to run a virus scan, update graphics, perform system background tasks, and more. For programs that need to run at a certain rate without interruptions, for example, cruise control system, this delay can cause system failure. That is very dangerous, right? In many real-time systems, they are made up of system on a chip. They are designed using this strategy. System on a chip allows the CPU, memory management unit, and attached peripheral ports to be contained in a single integrated circuit. They are less expensive than bus-oriented organization. Implementing a real-time system. We implement a real-time system by primitive priority-based scheduling. Important features are they must respond immediately to a real-time process, so the system must support priority-based algorithms with preemption. Priority-based algorithms assign priority based on their importance. Priority is the main concept in this in the scheduling, because we need to know what level of execution is to be done, what task should be given the highest importance. If scheduler supports preemption, a process currently running on CPU will be preempted if a higher priority process will be available to run. Solaris, Windows XP and Linux systems assign higher scheduling priority to real-time process. They will provide only soft real-time functionality. For hard real-time functionalities, we need additional scheduling features to meet timing requirements. Let's see the diagram of a scheduling. In the scheduling, we have three states. They are blocked, ready, and running. And the task performed by these scheduling is, in the ready states, we have all the tasks and they should be executed, right? In the ready, all the tasks will have some priority. Based on their priority, they are sent to the running state. Whenever a particular task comes to the running state must execute it. In the running level, if there are two or more tasks and if the other one is having high priority, that is again sent back to the ready state. And if the task in the running state needs some more information, some more resources, then it is blocked. That is sent to the blocked state. Here the tasks wait in the blocked state. It gets all the requirements for that to be completed. Then after getting all the information, that is sent to ready state, and again the same process continues and the program executes. Let's see the scheduling algorithms. They are cooperative scheduling, preemptive scheduling, primitive scheduling, earliest deadline first approach, stochastic digraphs with multi-threaded graph traversal. Let's see the conclusion of this presentation. The trend of using microkernels for real-time operating system are more likely due to the close relation between the real-time and embedded systems. Microkernels are also advantageous because they make it easier to minimize various overheads and to validate systems behavior. Systems will become more dynamic, though real-time operating systems will need to provide dynamic task admissions. Protocols, recovery mechanisms, overload handlers, and mechanism for monitoring and adapting to changing environment like network topology. The benefit of using real-time models are very real and absolutely necessary for some tasks. Even in areas where non-real-time tasks have sufficient, they are multimedia application sensor networks, moving to real-time tasks will increase system stability and predictability. Ultimately, various levels of quality of services are most easily guaranteed through real-time means. Real-time systems will play an increasingly important role in the computing as portable and mobile electronic devices continue to integrate themselves into the real everyday life. The main advantages, this is playing a major role in our daily lives. Thank you for watching this video.